Good morning. Today we are going to see about full adder circuit. So here we have the definition. Full adder is a combinational digital circuit that adds three binary numbers of single bit each and produces two outputs, namely sum and carry. So from the name itself, we know that it is a adder circuit, right? So it adds three single bits. That is important. Three single bits. We name them as A, B, and then CI, like that we have named, and these are all single bits. Then they are being added and we get the result as sum and carry. Okay, so these two are the outputs. So now we are going to see how to design this full adder circuit. For that we have to follow the 4 steps. The first one is block diagram, the second one is the truth table, third one is the Boolean expression, and the fourth and the final step is the logic diagram. So this is the block diagram. We can also call it as the logic symbol. Okay, we can name it also, we can name it as a logic symbol. So here you have the block. So this block has the full adder written inside, and then here you have this 3 inputs A, B, and CI. Okay, so these 3 are the inputs, and here we have the outputs. Okay, S and C naught. So S indicates sum and this C naught indicates carry output. Okay, that's why we denoted it as C naught. Then the second step is truth table. So we have to frame the truth table. As we all know that this A, B, C, I are the 3 inputs. Since we have 3 inputs, we can have 2 power 3 input combination. That means 8 input combinations are possible. So first we have to write the input combinations. So how to write the input combination? It starts from 0, 0, 0. Okay, because it is single bit A, B, C, I, and it ends with 1, 1, 1. So the first value for this is 0 of digital. If you want to write the digital value, it is, that means decimal value, it is 0. Then for this it is 1. For the second combination it is 1. Okay, so second combination is 0, 0, 1. So this is 0, this is 1. Then for 2 you can write it as 0, 1, 0. And then for 3 it is 0, 1, 1. It is nothing but the binary equivalent of this decimal, right? For 3, what is this? If you do the repeated division, it is 1. 1 times it goes, then remaining 1. So you write it as 1, 1. Similarly, 4, it is 1, 0, 0. Then 5, it is 1, 0, 1. And for the 6, it is 1, 1, 0. And then for the 7, it is 1, 1, 1. So here we have this 0, 1, 2, 3, 4, 5, 6, 7. For this we have written this input combinations. Okay. Then comes the output. So we have to decide the output for this. So it is nothing but adding these 3 single bits, isn't it? So we have to add A plus B plus CI for this 0 combination. So 0 plus 0 is 0. Then again 0 plus that 0 is, the sum is 0, no carry is being generated. Okay, that is the concept. So the second combination is, for the input we have it as 0, 1, 0, 0, 1. Okay, so we have to add the 0 plus 0. So what is this 0 plus 0? You get 0. Again plus 1. So you will get the result as 1, means it is the sum, and no carry has been generated, so it is 0. Then for this combination, that is for 2, it is 0 plus 1 plus 0. Okay, so 0 plus 1 plus 0. So the 0 plus 1 resultant 1, that 1 plus the 0, that you will get the sum as 1 and the carry as 0. Like that we have to proceed. So for this third, okay, for this value 3, 0 plus 1 plus 1. So what it is, 0 plus 1 plus 1, right? 0 plus 1 is 1 already. That 1 plus this 1, okay. So you will get the sum as 0 and the carry is 1. That's why we get this combination. Then for this 1 plus 0 is 1. That 1 plus 0 will give you the sum as 1 and the carry is 0. Then similarly here 1 plus 0 it is 1. Then again with that one if you add a 1 you will get sum as 0 and the carry as 1. One carry is generated. And this 1 plus 1 you get it, the answer is 1 plus 1, you will get the answer as sum 1, along with that the carry is generated. Okay, so you have to then add this along with this. Actually we put it like this, 1 plus 1 plus 0. So 1 plus 1 is 1 0, right? So actually this is the sum, right? This is the carry, and this sum is to be added with this 0. So 0 plus 0, it results in 0 only. Okay, so the sum is, final sum is anyhow 0, and this is your carry already generated. So your answer is 0 plus 1. And then 1 plus 1 plus 1. Okay, so we have 3 ones. So how we'll get it? So 1 plus 1 plus 1. So for this 1 plus 1, you get the sum as 0 and the carry is 1. Okay, this is sum and the carry generated. This sum is to be added with this one. So you get again the sum as 1, no carry generated out of it, but already we have this carry. So this is your new sum. So the resultant is 1 plus 1. Okay, this is how we are deriving this outputs, but I can give you one more shortcut if you want. That is, see, another shortcut for writing the combination also. We have ABCI, right? So it is a 3-bit. So I already told you 2 power 3, 8 combinations are possible. So for that you have to start writing from 0, 1, 2, 3, 4, 5, 6, 7, isn't it? So for that, if you start from this LSB bit, it is 0, then it has to toggle. Okay, change often for each and every. So 0, 1, 0, again 1, 0, 1, 0, 1. Like that you have to write. Okay. Check this, 0 1 0 1 0 1 0 1, like that. But for the next bit you have to write 2 zeros followed by 2 ones, 2 zeros followed by 2 ones. So it is very easy for you to write the combination 1 1 0 0 then 1 1, like that you can. Then you have to write 4 zeros followed by 4 ones. So what it is, 4 zeros followed by this 4 ones, then you get all these combinations. This is how actually we write the input combination in the easiest way. Okay, now similarly I'll tell you how to get the output. So here if you have all the values are 0, sum and carry would be 0. Okay, but if you have odd ones, okay, here you have odd ones, so sum is 1. Here also you have odd one in this combination, so sum will be 1. Okay, carry would be 0. Here also you see, here only 1 1 is available, single 1 for this combination, so sum is 1, carry is 0. And anywhere else, no, single 1 is not available. Okay, so you have to check for the single one. For that the sum will be 1 and the carry will be 0. The second one is, if you check for 2 number of ones, if you have 2 number of ones, for that case sum becomes 0 and the carry will be generated. So here also you have 2 ones. So for that sum will be 0, carry will be 1. Here also you have 2 ones, so sum will be 0, carry will be 1. And the next third combination is 3 number of ones. Okay, so 3 number of ones, for that the sum and carry both will be 1. This is how we have developed the sum and carry outputs. Okay, so what would be our next step? As we all know, the next step is writing the Boolean expression, isn't it? We have to write the Boolean expression. So for that, what is important? We must know that the sum and carry output must be returned, right? So for that sum output, you will get one Boolean expression, and the second expression corresponds to this C0 carry output. So first let's check with the sum. So for that sum output, we get one here, again another one here, and so 4 ones are available here for the sum. So for this one, what is the input combination? It is 0, 0, 1. So it corresponds to A bar, B bar, Ci, isn't it? So it is A bar, B bar, Ci. The bar is represented as dash. Okay. Plus the second combination for this is A bar, B, Ci bar, isn't it? So 0 represents bar, and if it is 1, the same literal, we can write original literal. Okay, so the second combination 0, 1, 0. So 0, 1, 0 means it is A dash, B, Ci dash. Okay, then the third combination is this one. For that, the input combination is A, Bi dash, Ci dash. Okay, so the third one is A, Bi dash, Ci dash. Plus the last one is this combination 1, 1, 1 that corresponds to ABCI. So this is how we get the sum output. The second one is C naught output. Okay. So how to write the C naught output? For that, we have to verify the C naught column, and in the C naught column we get one for this one, this one, this one. Okay, so it corresponds to this, isn't it? This one corresponds to, so it is A dash, then we have this B, then Ci. This is our first. Second one is this. For this one, it is the input combination is 101. 101 represents A, B dash, Ci. Okay. Then the next one is that corresponds to 110. So 110 means it is, we have to put plus. Okay. That is A, B, Ci dash plus the last, this one that corresponds to the input combination A, B, Ci. So if you once again check this sum and carry outputs, okay, we can notice that this A, two literals will be having dashes, bars. Here A dash, B dash. Here it is A dash, Ci dash. Here if you see B dash and then Ci dash, this is B dash. Not B dash, Ci dash. Okay. So two literals will be having the dash. Okay. And the last term will be the literals will be original A, B, Ci dash. Similarly, in C naught also we have the last one is the original literals. But here the single literal will be having its bar. Here A bar, here you have this B bar in the second term, in the third term it is Ci bar. Like that we got it. Okay. So now we got this sum output and the carry output. Okay. So for this you can draw the logic diagram, which is the next step. We know that, okay, we have to draw the logic diagram. But using the basic gates, if you draw, that's the last step, the logic diagram. So what you need to do, you have to draw 3 input lines. 1, 2, 3, and we name them as ABC, A, B, Ci. Then each and every term we have to take, right? So the first one is A bar. So you take a line from here. We take a line from A, and we take a line from B, we take a line from C. But A bar, B bar we have, so I'll draw this inverter in both the cases, and then we go for this. These 3 literals are combined. These 3 are combined using dot, isn't it? AND gate. So here we have the AND gate. This is how we get the first term. It's over. When you go for the second term, so there you have this A bar again, and then B original literal. Okay. Then Ci bar. So we put an inverter, and then they are the second term is combined using AND gate. Then the third term, we go for the third term, it is A and then B bar and then the C bar, CI bar. Okay, so we combine them using AND gate. And the last one is the original A, B and then CI. They are combined. And these four terms are combined using this plus, isn't it? These four terms are combined using this plus. So what it is a OR gate. So we draw the OR gate. So this is how we get this sum output. Yes. Similarly, we go for the carry output. So for the carry output, for that also we have to take the lines from here itself. For that, the first term, what is the first term? It is A bar B C I. The last term for the sum and the carry output are the same. So this is the last term. From that we can take a connection. One term is over. Okay. And this is the first term, we have A bar, right? So it is A bar, we put like this, then BCI. So it is B and here C. From C we have taken connection. Here it is A, as B it is A. So they are combined using this AND gate. Then the second term, A, B bar, CI, right? So it is A, then B bar, then CI. Then they are combined using this AND gate again. Okay. Then the third term is ABCI bar, isn't it? ABCI bar. So for that, A, B, then the next one comes from here, CI bar. Okay. So these three are combined using AND gate. Again, the last term comes from here. So we take the connection from there also. So these four terms are combined using plus. So it is OR gate. So this is your carry output. This is how we get this logic diagram. Okay. So that is done clearly, neatly in the next slide. Okay. So this is the logic diagram using basic gates. The same thing which I have drawn earlier, right? Now, usually people will go for the simplification of Boolean expression using K-map. After that, the simplified expression will be drawn as the logic diagram because you'll need minimum number of gates in that. Okay. So we go for the next step as the simplified Boolean expression formation using the K-map. For that, we have, as we all know, we have three inputs. So three inputs A, B, C, I. For that, how many three variable K-map is needed. So this is the model for a three variable K-map. So here you put the one input A. This is BCI on this other side. And for this A, you put 0 and 1 here. And for this BCI combination, we put 0, 0, 0, 1 and then again 1, 1 and 1, 0. This is the gray code actually. Okay. So in gray code format, we write this values and we have how many cells? We have actually 8 cells. Each and every box is a cell. This is a cell. This is another cell. This is another cell. So we have actually 8 number of cells or 8 number of boxes. Each box represent a value. This box is 0. This is 1. This is 3 and then this is 2. Actually how it comes? If you write this value which is available here at this point, this corresponds to this 0 and this 0, 0. So it is 0. First you write this and then this 0, 0. So 0, 0. So that represents 0. Okay, binary value 0, 0, 0. Its equivalent decimal is 0. So next one is if you go for this 0 first and then followed by the 0 1. So how do you write 0 0 1? So that represents the 1. Okay, so like that we have all these binary values converted and given the decimal value. You can check this also. This is 111. Okay, so that we got the 7. So how we write? It is 0 here, 0 1, then you have to put 2 3, then 4 5 6 7, like that we are writing. Okay, this you might have learned in your K-mark. Anyhow, so we have already got the Boolean expression for the sum and carry, and we know that so this is for sum and carry output. We had the expression. So this expression is to be actually simplified. So the first term, what is the first term here available? So the first term available is a bar, b bar, c, I. So that corresponds to 0 0 1. That value is 1. So this is 0 1 0, right? It is 0 1 0. So that corresponds to 2. And this is 1 0 0, that corresponds to 4. And this 1 1 1, that corresponds to 7. So we can write the sum as min term like sigma s is equal to sigma 1 comma 2 comma 4 7. In the same way, the C0 can be written like it is. This is 0 1 1, so that represents 3. This is 1 0 1, that represents 5. 1 1 0, that is 6. 1 1 1 7. We had done it in the if you go back and check your truth table, here we have actually represented this as 0 1 2 3 4 5 6 7, like that we have already represented, right? So for that correspondingly you have the sum values as 1. So from that also you can write the min terms directly. See here you have a 1 that corresponds to 1. This one corresponds to 0 2. So you can write this corresponds to 1 sigma m 1 comma 2 comma, and this one corresponds to this 4, and this corresponds to this 7 value. Like that we can write. Okay, because we need this min term, that is for S. Similarly for C0, if you check, so here you have a 1 that corresponds to 3. So for carry output it is sigma m of 3 comma, then here you have that corresponds to 5, and then next one is 6, next one is 7. Like that we can easily write. Okay, so go for this. So what this C0 is sigma m of 3 comma 5 comma 6 comma 7. Now inside this K map for S, this is the K map for C0. Okay, this is the K map for S, this is the K map for C0. So for S we have to refer this. This is 1 2 4 7. So for that one value you have to put a 1. Then for this second cell, okay, the cell which is numbered as 1 2, you have to put a 1. And then it is 4, so you put a 1 here, and then you have a 1 for the 7, so put here. So you have ones here. So we cannot combine these ones together because they are not adjacent ones. So we can simply put them like this. So we have 4 single loops. And for that, if you write the expression again, you will get the same, right? So this cannot be simplified. This S cannot be simplified. Okay. So for the S, we get the same expression like this only. So this cannot be simplified using K-map. It is not possible. So we can go for alternate method. So what is the alternate method? The next method is using Boolean laws or theorems. We can do it. Okay. So for that we'll again take this sum alone. I'll take it with this. Okay. So if you take the sum, now S is equal to A bar B bar Ci plus A bar B Ci bar plus A B bar Ci bar plus AB. So anyhow we need to have the simplified expression. Okay. So we want to have the simplified Boolean expression. So for that now I am going to adapt this Boolean laws and Boolean theorem method to simplify it. Okay. So in this case, if you see, if you take A bar outside from these two terms, what you get? First term contains B bar Ci plus second term is B Ci bar plus here if you take consider these two terms, there you have A as common, so that I can write B Ci B bar B Ci bar plus B Ci. So what is this actually? It is A bar into B XR Ci, isn't it? Because it is B bar Ci plus B Ci bar is nothing but B XR Ci plus here you have A. Here if you see it is B bar Ci bar plus B Ci means it is B XNOR Ci. So we know if we take this X as B XOR Ci, then we know that this X bar is nothing but B XNOR of Ci because these two are complement of each other. So I'm going to substitute this X here. So it is A bar into this term becomes X plus this is A into this term becomes X bar. So once again, if you check, it is nothing but again exclusive R, isn't it? So A exclusive R with that X. So in place of X, if I substitute, I'll get it as B XR Ci. So this is the final sum output which we need. Okay. This is the simplified expression we got. A exclusive R with B exclusive R with Ci. So that is neatly done. In the next page, we check here. So I have done it. This is the expression we got out of this truth table. After that, out of these two terms, I have taken this A bar outside so that you get this B bar Ci and this B Ci bar. Out of these two, I have taken this A as common so that we get this B bar Ci bar plus BCI, and in this we get this A bar here and this can be written as B exclusive OR with Ci, and here this A is taken here, and for this we can write it as B X NOR with Ci. Okay, so we have got this. Yes. Then we want to actually simplify the next one. Next term, next expression is the carry output, right? So we want to get it. The carry output must be simple. So for C0, it is 3, 5, 6, 7. So I put ones here. 3, 5, 6, 7. Already I have placed here. So this can be combined like I can combine these two. Then I can combine these two once, and then I can combine this. Okay, so for this red color, how we'll write it? For this red color loop, we formed three loops. This is the first loop we did. Okay, so on this vertical side, the 0 and 1, it is cancelled. So we got this 1 and 1. So that corresponds to this BCI only. Okay, so when you go for this green color loop, this loop here, it corresponds to this one that represents your A, and on this side if you go, it is 0 1 and 1 1. So in that, the 0 and this 1, that means B get cancelled, only CI remains. So that gives you ACI. And for the last loop, it is the blue color loop, right? So for this loop, if you check, corresponding to that, we got this A, and on this side we have this 1 and 1 that represents your B. Again here 1 and this 0 get cancelled, so it's gone. So what is the three terms we got? One is BCI plus this ACI plus this AB. These three terms we got, right? So these three terms are obtained as a simplified one out of this K map, but still we need some other format so that it is easier for us to get the logic diagram. So what we are going to do now is, this BCI is missing the literal A. So I'm just going to modify it using this A plus A dash. So what is it? A plus A dash, any literal plus its complement gives you the value 1, so that this term is not getting changed. Okay, so we are adding this A plus A dash so that this particular value is not changing. So BCI. Similarly, when you go for the second term ACI, in that which literal is missing? B is missing, so I am going to write it as B plus B dash, which is 1 actually, right? So that term value is not changed, and plus we are going for the last one, it is AB, last term. So then I am going to distribute it so that I am getting this as first. Okay, so it is ABCI plus the second term along with this. If you multiply, then you get A dash BCI plus this plus I have taken now. Then this multiplied with this B and CI, right? So it is A B CI plus next one is A B dash CI. So it's over now, plus this AB is there. In this, if you check, we got this ABCI 2 times, right? So if you get X plus X, that is equal to X, single time you can write. Similarly, we got ABCI single time and second 2 times. So you can write it as a, it's enough to write it for a single time. The second term I am writing A dash B CI plus A B dash CI, this term, this override, plus AB. If you consider these two terms, okay, that's the next step. A B CI. In this, CI is common, so that it becomes here also CI, here also CI. So I have taken the CI common. So the remaining is A dash B plus AB dash out of this, isn't it? This is your A dash B I have written, and this is your AB dash which I have written. Okay. So we have written this. After that, you got this plus AB, this term I'm writing. Now I'm going to combine these two, ABC and AB, because AB is common in that. So AB into CI plus this becomes 1, right? Because we have taken AB outside, plus CI into A exclusive OR with B, because it is A dash B plus AB dash. It is A exclusive OR with 1 plus anything is 1 plus x is equal to 1. That is one law we have, right? 1 plus x is equal. So 1 plus CI becomes 1. So that we got it as AB plus CI into A exclusive OR with B. Okay, so this is the simplified expression finally we get for this carry output. So this is also done neatly in the next page. Okay, so I have done it in this. So we got it. Okay, this carry output. So for the carry and the sum output, we have to draw the diagram, logic diagram for the simplified one, isn't it? So how to do this? So we got this already. We got this. Okay, these two expressions we got. So the first we have to write this ABC and we have to draw 3 lines. Let me put it. So A, B, C, I. Then you will draw 3 lines for the logic diagram. Okay. For the simplified expression. And what is the simplified expression for S? For S it is A exclusive OR with B exclusive OR with C. So first we take the connection from here. A exclusive OR with B. This is actually you can do it with all these things, but we go for this kind of representation. First you will exclusive OR this 2 alone. After that, this resultant A exclusive OR with B is exclusive OR with CI. So we got this result, right? That would be exclusive OR with the CI. So what do you get now? We get this sum output. Okay. What is the carry output we got as a simplified one? It is AB plus CI exclusive CI into A exclusive OR with B. This is what we got. Okay. So if you check this at this point, okay, at this point we get this A exclusive OR with the B. So this term is already available. Okay. As a logic part, logic diagram, it is available. So I'm going to take the connection out of this. This is this A exclusive OR B is over, and the CI. So this is also we got already, right? So the CI. So they are combined using AND gate, right? So it's over. This part is over. Then the next one is AB. So for that AB, I can take the connection from here. A, and then this is B. So you got another AND gate. So this part is also over. Then we have this plus. Plus is nothing but this OR gate. So using the OR gate, we can do it, right? So it is your carry out. So this is what shown here. If you check, it is clearly drawn here, right? XOR gate A exclusive OR with B. So you got the first term. This is over. Again to combine with the CI using this XOR. So the CI is taken and XORed. So you get this final. And when you go for the second output, that is C0 output, first we have taken the A exclusive OR with B. So this is taken from this connection. Then CI is ANDed. Okay, so CI is given AND gate. This is over. This part is over. Then this AB. So we have taken the connection which is ANDed. So this part is over. Then again the plus sign. So we got the OR gate, that it is over. Okay, so we'll see the same type of implementation that is also important, that is full adder using two half order circuit. Okay, that is also important, that we'll see in the next video. Okay, thank you.